Okay, we're going to start a new unit. By the end of this unit, I will be back in school, and you'll be saying thank you and goodbye for now to Miss Woodlock. But in the meantime, at least some of this unit I'm still going to miss. So we're going to take a look at your calendar on page 5 of your book. We're going to mark the days of this unit in your calendar, and we're going to go from there. So depending on if today's an A day or a B day, you should be either A day starting this unit on the 6th or B day starting this unit on the 11th. And my calendar, when I printed it, was a little messed up where we had the PSAT day in the wrong week. Yours should be fixed already. And currently when I'm recording this, if you're A day, you should be taking the Unit 4 test on the 24th, which is the day before the PSAT. If you're B day, it's going to be on the 26th, which is the day after the PSAT. That may change between when I'm recording this and when you're watching it, and if it has changed, Miss Woodlock will let you know. But go ahead and mark your start day of the unit and your test days of the unit, unless Miss Woodlock tells you to mark something different. And as usual, there will be 2 quizzes in this unit, and at this particular moment in time, as I'm recording this, I'm not positive which days those quizzes will be on, but again, Miss Woodlock should be able to tell you that, so you can write that down as well. Once you're done marking your calendar, please turn to page 31, which looks like this, page 31, and you're also going to need 4 colors today. I am going to use pink, orange, green, and blue. You can use any 4 colors as long as you use them consistently. But if you want to be the same colors as my colors, then it'll be pink, orange, green, and blue. Just so you know. So on page 31, we're starting a new unit today. It's about electrons and where you can find electrons inside of the atom. So we have talked about before that electrons are in the electron cloud, where we talked about, like, okay, there's a nucleus, and then that's where all the protons and neutrons are, and then outside the nucleus is what we call the cloud, where the electrons are. And we've so far this year stuck to the Bohr model, or the planetary model. But back in Unit 2, when we first talked about the planetary model, I pointed out that that's not what atoms really look like, because that's a 2D model and atoms are 3D. Well, this is the unit where we're going to talk about the 3D atom, what that really means. So, electron orbitals are the locations where electrons are found. They are part of the electron cloud, and each orbital holds 2 electrons. Now there are 4 kinds of orbitals, and this is where we're going to start our color coding. There are 4 kinds of orbitals, and they're all named after letters. So we call them S, and this is a lowercase s, and P, and D, and F, and these are all lowercase letters. Again, S, P, D, F. And again, this is where I'm color coding. So I'm using pink for S, orange for P, blue for D, green for F, kind of arbitrarily. Doesn't really matter. Just as long as you stick to the same color for each letter for everything we're doing, you'll be fine. So let's talk about S first. They're called S orbitals because they have a spherical shape. So you can draw kind of a sphere, like a circle, put a center in it, do that thing so it kind of looks 3D. Their shape is spherical, and that's because S basically stands for sphere. Get it? And there is one s orbital in every energy level outside the atom. So basically, these different rings we would draw in the planetary model are showing us a distance from the atom, and each one of those rings has one s orbital, one sphere, where electrons can move around. Since each orbital holds 2, if there's one orbital and it holds 2 electrons, that means there are 2 total electrons that can be held within an s orbital at whatever distance from the nucleus we're looking at. S orbitals have low energy, and there's a better picture of it here, where basically it's a sphere, and whoops, if we zoom in here, there, it's a sphere, and so we've put a picture where it's on the XYZ plane, just so you can see, oh look, it's 3D, it's in 3D, that's the point we're getting at, it's in 3D. Okay, switching colors, we'll talk about p orbitals. P orbitals kind of look something like this, and you can think of it as being P for peanut. There are 3 p orbitals in every energy level that can have them. And since each one of those can hold 2 electrons, that is 6 total electrons in the p orbital. So if we go back and look at the planetary model, the first energy level only has s. The second energy level has s orbital, but it also has 3 p orbitals. So it's like, here's a peanut, there's a peanut, there's another peanut coming like forward and backward. And I know my art is not very good, but that might help you a little bit to think about what it looks like. Where basically, in each one of these, like there's 2 electrons moving around here, there's 2 electrons moving around there, and there are 2 electrons moving around here. And there's also 2 electrons moving around in the sphere. And that is the 8 electrons that can fit in that second energy level. Remember, going back to middle school, you learned like the first shell holds 2, the next shell holds 8, the next shell holds 18. Well, this is where this comes from. The 8 that go in that second shell, 2 of them are in that s sphere, and the other 6 are in these 3 p orbitals, 2 electrons, 2 electrons, and 2 electrons. And again, I'll zoom in here. So there are 2 electrons that move around in each sphere, and there are 2 electrons that move in each one of these different peanuts, where one of them's horizontal, one of them's vertical, one of them's front and back. I know this is a little weird, like I'm aware that this is a little weird, but this is actual real life. Like, if we had a multi-billion-dollar microscope that could show you something this small, this is actually what it would look like where the electrons are moving around. Microscopes don't currently exist that can visually show you this, but we have a lot of data from math and experiments and stuff that verify that, like, yeah, this is what it really looks like. And one day, maybe you will invent a microscope that actually can zoom in enough to show us this is real. But I promise, the science is there. This is what they look like. I know it's bizarre, but it's also true. Sometimes science is just weird. Anyway, p orbitals have medium energy. And let's talk about the next one, d orbitals. So this is where I'm switching to blue. D orbitals, most of them look something like this. And you can think of it as D as in like a daisy, cute little flower. There are 5 of them in each shell. So they're all like looking kind of like this over here, but they're turned different ways. So there's one of them that's like this way, and then the next one's flipped like this way, and the next one's flipped like that way, and so on. Each one still only holds 2 electrons, so total we're looking at 10 electrons. And they are high energy. And they start existing in that third shell. So like you got your nucleus. There's your shell that has just an s orbital for those 2 electrons. The next shell has 8 electrons, and that's from the s, the 3 p's altogether. So that's 2 electrons in the s and 6 in those peanuts. So that's 8 total electrons. That third shell that can hold 18, well, guess what? That's 2 from S, another 6 from these 3 P's, 2, 2, and 2, and then another 10 from the 5 different daisies you can have. 2, 4, 6, 8. I didn't leave myself enough room, but there you go. That's where those 18 come from, is 2 plus 6 plus 10 from 1 sphere, from 3 peanuts, and from 5 daisies. So again, when they taught you that in middle school, 2, 8, 18, like this is where those numbers come from. I know, it's mind-blowing. And then the last one, F orbitals, I'm not even going to try to draw them because they are flippin' crazy. Or I don't have room to write the word crazy, so I guess I'll write nuts. They're flippin' nuts. Okay, and here I'll zoom in on this picture so you can see it real well. But basically, they're all over the place. You can kind of tell even just from this crappy picture that like it's just everywhere. So I never even try to draw them. If you really want to like Google image search it yourself, be my guest. But they're flippin' nuts. There are 7 of them. Again, each one holds 2 electrons, so that is 14 total electrons. And their energy is very high. We're going to come back to the colors. Don't put them away. But you can put them aside for the moment, but we will come back to them. Okay. We got to keep in mind what each of these things mean. We're going to come back to these as well, but we need to do some other vocabulary first. So there is something called orbital notation, which shows what electrons are in which orbital, which electrons are in which orbital. This is basically a diagram. When we do orbital notation, we always start at the lowest level. Think about it as electrons being lazy. They start at the bottom and then work their way up if they have to. This is called the Aufbau principle because the word Aufbau is a German word because it was some German guys who decided how to make these diagrams work. The word Aufbau is a German word that means filling up. So you start at the bottom and you fill your way up the diagram. When we draw these diagrams, 1 arrow represents 1 electron. You can have 2 electrons go in each orbital, which, again, we set up here. Each orbital holds 2 electrons. And because of that, if you have 2 electrons in each orbital, and we're showing orbitals as blanks, then that means you can put 2 arrows in each blank. And it'll always be an up arrow is 1 electron, a down arrow is 1 electron. And that means, here, we have a blank, we put an up arrow and a down arrow. The blank is an orbital, and then each one of these arrows is an electron. Each one of those arrows is 1 electron. The 2 arrows must have opposite spins, meaning one of them has to be up and the other has to be down. And that's because if you put 2 electrons in close proximity to each other like this, like in real life, I mean, I'm talking about like literally inside the atom, electrons are both all negative. They repel each other. So if you put them next to each other, then they're going to repel. But if you force them to stay in one area next to each other, they can't just push apart. So the most they can do is they spin in opposite directions. Like one of them will spin clockwise and the other one will spin counterclockwise. I think I just did that with my pen backwards from what I was saying out loud. But basically they spin in opposite directions where one's going counterclockwise while the other is going clockwise. This is very hard for me to do, actually. You can try it, spinning 2 pins in different directions at the same time with each hand. That was difficult. I should not have tried that. Anyway, they repel each other and they spin in opposite directions because of it, trying to avoid each other. And so in our diagram, we have to reflect that, where if one of them's up, the other has to be down because they're always moving opposite the way the other is. This thing where they have to have opposite spins, that's called the Pauli exclusion principle. Pauli was a dude, and basically he was saying that they are trying to exclude each other, so they spin in opposite directions. Just as a rule, we always put up first, and then the second one will be down. There's also what's called the good mother rule, which I'll read this right now, but I'm going to come back to this later. Each orbital must have 1 electron before you add a second electron at the same level. This is also called Hund's rule, and we're going to come back to that. Okay. Here's a diagram that can help us make an orbital notation diagram. And we always read this diagram like a book from left to right. So it always goes like here. You start at the top. I should say start where helium is. Or sorry, hydrogen. Start with hydrogen and then you move across. And then you come back over here and move across. And then you come back over here and move across. Just like if you were reading a book. You read to the end of the line, then you go to the next line and read to the end of the line. And we just keep moving across and across. And it gets a little weird with these guys, but we're not really going to worry about those down there. Anyway, you just keep moving across. So here's where I want to color. One place I want to color. There are regions on the periodic table that go with each type of orbital. So like these elements in this region where everything's labeled S, these elements all have their what's called valence electrons. We'll talk more about those later in the unit. Sitting in a sphere, in an S orbital. So these are our S's. Notice that for every S level, there's 1S, 2S, 3S, 4S, 5S, 6S, 7S. For every S level, there are 2 elements, and that's showing that for every S, there are 2 electrons as well. So like 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and so on. These numbers in front, 1s, 2s, 3s, 4s, that is telling you how far from the nucleus you are. So like, if this is my nucleus, 1s would be the first shell outside the nucleus. And then the next shell out would be where the 2s is. And the next shell out would be where the 3s is, and so on and so forth. Pick up whatever color you used for P at the top. I had used orange for P, so I'm going to pick up my orange. And let's color the P's also. This is my P area. It was like a kindergarten level joke. These are my P's. And again, this region is telling me that these elements over here, their valence electrons are in this P section. So you'll notice there's in each row 1, 2, 3, 4, 5, 6 elements. That's corresponding to the 6 electrons that we have spread out in our 3 peanuts, 2, 4, 6. And again, if we were looking at what these numbers in front mean, like this 2 right here, that means there are, in the second level, there are 3 2Ps, like 1, 2, 3 for our 6 elements. Or in the 3P, we've got out at the 3rd energy level away from the nucleus, there are 3 peanuts, 3 orbitals. The D section, I used blue for my D, so I'm going to pick up my blue. I'm going to color the D's. And again, if we count here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. That's corresponding to the 10 electrons that are total in all my daisies. Because I have 5 daisies, each with 2 electrons, that's 10 total electrons. So it's that same idea. So in this 3rd energy level, the fact that this is 3D tells me that in this 3rd energy level, not only was there a 3s, one sphere in that 3rd shell, basically, and not only are there 3 peanuts in that 3rd shell, there's also 5 of the daisies in that shell. That's what's going on here. It's kind of hard to read. I don't think that really made it better. Okay, for the last one, this bottom section is where the F orbitals are, those flippin' crazy ones. I'm going to color these green. I used green for my F. And again, if you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements. That's corresponding to my 14 electrons that are shared in my 7 flippin' crazy orbitals. And you'll notice they start in the 4F, which means we'd need like a whole nother shell out here to label all 7 of where my F orbitals are going to go. Okay, again, I know this is weird. Like, I'm fully aware of what a strange bit of chemistry you are learning right now. And it is probably the weirdest thing we're going to do all year, but I promise once we get a little practice with it, it's really not that bad. So now what I want you to do is I want you to go to your periodic table that's on the back of your book. I want you to color code that as well. So I'm going to go ahead and do mine. You use your colors. I used pink for S. So I'm going to draw myself like a legend. Draw myself a legend. S, P, D, F. My S's are pink. So I'm going to color all my S's pink. I know your periodic table is not on white paper, so yours might end up looking a little more complex than mine, but you'll be fine. I have faith in you. Okay, and don't forget helium over here is also S. So there's all my S's. And you also may find it worth labeling, like this is 1S. Well, I'll do that with my marker. Specifically 1S, 2S, 3S, 4S, 5S, 6S, 7S. Okay, I used orange for my p orbitals, for my peanuts. So I'm going to color all of those orange. That's this section over here. And I'm going to make sure and add orange to my legend as well. If you're using markers, please don't color so dark that you can't see what your periodic table says. You still need to be able to like read your periodic table. I would just like to point that out. If you're using marker, you might want to just like highlight the outside instead of coloring over everything to where you can't read anymore. Just a thought. Notice the S's started at 1, but looking back on our chart on page 31, the P's start at 2. So this is 2P, 3P, 4P, 5P, 6P. My D's, I used blue, so I'm going to color those. Do, 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 do. Da, 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 da. I know I colored outside the lines. Sue me. Don't sue me, please. I don't have any money. I'm a public high school teacher. The S's started at 1, the P's started at 2, the D's start at 3. So this is 3D, 4D, 5D, 6D. Oh, and don't forget to add D to your legend. And finally for F's, I used green for my F's. So I'm going to add that to my legend and then color my F's green. Yay for coloring. This is so therapeutic. And the S's started at 1, the P's started at 2, the D's started at 3, the F's start at 4. You may have noticed a pattern. It's a fairly simple pattern to follow. Okay, when you're done coloring your periodic table, let's actually go apply some of this back on page 32. On page 32, we have a diagram. We're going to skip that stuff at the top and come back to the stuff at the top. Here's a diagram of orbital notation. Remember, each line represents an orbital. Each arrow represents an electron. You fill from the lowest energy going up. So for example, we're going to do oxygen. And the first thing you need to do is figure out how many electrons you are going to need to draw. So if you remember, we go to our periodic table. And we learned something back in Unit 2 that told us how to look at our periodic table and tell how many electrons there were. We called it Ape Man, where the ape said that atomic number equals the number of protons equals the number of electrons. So So if we look at oxygen, oxygen has an atomic number of 8. That means 8 protons and 8 electrons. So for oxygen, we need to draw 8 electrons into this orbital diagram, orbital notation diagram. We start at the lowest energy and go up. And if we're going to draw 8 electrons, that means we're drawing 8 arrows. So we go to this bottom orbital. We draw an up arrow. That's 1. Each orbital can have 2 electrons in it, because remember, each one of these blanks is an orbital. Each orbital holds 2 electrons. So if I draw 1 arrow, that's 1 electron. I can draw a second arrow, and we have to remember that each orbital, you should have 1 up and 1 down. So there's my up, and here's my down. Okay, that's 1, 2 electrons, 2 arrows, 2 electrons. We need 8. So now I go to the next highest orbital. And I go, here's an electron, here's an electron. 1, 2, 3, 4. Again, I need 8. So now I come up to this 2p. That's the next highest up. So we start at the bottom and we're working our way up. Now, we put in this first arrow here, and then something weird happens. And this is where I want to come back to that idea of the good mother rule, also called Hund's rule. And the good mother rule says that you have to have 1 electron in each orbital, meaning 1 arrow in each blank, before any get a second electron. And essentially what that means is, think of it this way. Let's say your family moves into a mansion. Okay, a mansion, like Downton Abbey kind of mansion, where it's like, there's this giant entryway, here's a bunch of windows, you've got like, let's say it's a huge, huge mansion with like 30 bedrooms. Okay, your family moves into a mansion with 30 bedrooms. And when I say your family, I just mean like the people you currently live with. You move into a mansion with 30 bedrooms. And your parents or your grandma or whoever the head of your family is says, okay, everybody, now we live in a house with 30 bedrooms. We're all going to pick 1 bedroom and all of us are going to sleep in that together. You'd be like, what about the other 29 bedrooms? And your mom would be like, those are for guests. You don't need your own room. We can share 1 bedroom. Those 29 other rooms in our mansion are for guests. You'd be like, no. If there are 29 empty rooms, I'm not sharing a room with you, Mom and Dad. Gross. I'm a teenager. I need some privacy. Oops. So that's sort of the idea behind the good mother rule. You'd be like, I'm not sharing a room if there's all these empty rooms. And the electrons are the same way. They're not going to share a room if there are empty rooms. So when I get to this 5th electron, it gets its own room. I need 8 electrons. So when I get to my 6th electron, is it going to share a room when there's 2 empty rooms it could have? No, it's not going to share. So it's going to move and get its own room. Same with my 7th electron. My 7th electron could share here or here, but there's a whole empty room here. Why would it share if there's an empty room? It's going to come over to the empty room. And then my 8th electron, then it's like, okay, now there's no empty rooms. Now I have to share. I get it. There's no empty rooms. I guess I have to share with somebody. So it'll go be in that first room. And remember, one of them's up. The other one has to be down. I'd like to point out the order that this diagram goes in. We started at the bottom with 1s. And on the periodic table, 1s is where we start. We moved across, and we were still 1s. So that's 2 electrons, 1, 2. Each element tells me how many electrons go in that section. So 1s has 1, 2 elements. That's 1, 2 electrons. And that's what we did here. 1s had 1, 2 electrons. Then we moved to the next row, which was where 2s is. So we moved to 2s. 2s has 1, 2 elements, so we drew 1, 2 electrons. Then we came across to where 2p started, and in the diagram we moved up to 2p. Remember, we were trying to get to oxygen, which is the 4th element right there. So we did 1, 2, 3, and oxygen was number 4. We did 1, 2, 3. There's number 4, and that's where we stopped. So this diagram is going in order of the periodic table. And I'm just pointing that out because eventually you're going to take a quiz on this and you don't get a blank diagram to fill in. You have to be able to use your periodic table to figure out what order these are supposed to go in. Now, drawing the diagram like this takes a lot of space. So normally we'll make it take up less space. We'll kind of squish it by drawing it just going horizontal. Like here's my blank for 1s and my blank for 2s, and then here are my 3 blanks, my 3 orbitals for 2p, and then I can fill them in like this. You don't have to, but this does save a lot of space if you go across like that. I also want to point out that each of the S's on this diagram is only 1 blank. That's because there's only 1 sphere. Each of the P's has 3 blanks in it. That's because there are 3 peanuts. Each of the D's has 5 blanks in it. That's because there are 5 daisies. There's a reason for everything in this diagram. Let's turn the page and look at page 33. Oh, not 33. Keep going. 34. I want to do a couple of these with you, and then I'll give you some time to work on some others. Okay. I want to do with you, I want to do boron with you. I'll do neon with you. And I'll do, is there a harder one on this page? Yeah, iron. I'll do iron with you. So I'm going to do these 3 with you, okay, right now. And then you'll have some time to try orbital notations for the rest of this page and the next page on your own. So let's look at boron. First, we need to know how many electrons. If we go look at a periodic table, again, remember ape man. Atomic number equals your number of protons equals your number of electrons. So if we go look at boron on the periodic table, its atomic number is that top number. So here's boron. Its atomic number is 5. There are 5 electrons. And you can do this looking at this original diagram if you want to try and figure out what order they go in. But I recommend using your periodic table because, again, you're not getting a copy of that diagram when you get to your quiz or your test. So remember, we always start at hydrogen, which is in the 1s section. So the first thing I'm going to do is I'm going to write 1s. And how many blanks do s's get? S's get 1 blank, so I'm just going to draw 1 blank over it. And each blank gets 2 electrons, an up followed by a down. So I draw that also. But that's only 2 electrons, I need 5, so I have to keep going. After 1s, I'm supposed to go down to the next row. The next row, this section is 2s, so I'm going to write 2s. Again, how many blanks do s's get? S's get 1 blank, so I'm going to put 1 blank over it. Each blank gets 2 electrons, an up and a down, so I fill those in. And that's only 1, 2, 3, 4 electrons. I need 5, so I got to keep going. If I look at my periodic table, after 2s, I'm supposed to go across here to this section, and this section is my 2p section. So I write 2p. And if I check my notes, there are 3 peanuts. That means I need 3 blanks. 1, 2, 3. Each blank can have 2 electrons, but remember, we're only going to 5. And then we stop, because once we get to 5, that's boron, and we stop. So I'm just going to stick 1 right here and call it a day. These other 2 blanks just stay empty. Yes, even though they stay empty, you still have to draw the blanks. Because you have to prove to me that you know that there are supposed to be 3 blanks when you're looking at peanuts. Let's look at neon. Going to your periodic table to figure out how many electrons neon has. Check neon's atomic number. Neon has 10 for its atomic number. That means 10 protons and 10 electrons. Again, when I start my diagram, I always start where hydrogen is, which is in the 1s. And it moves across to still be the 1s. So the first thing I write is 1s. Again, s's always have 1 blank. So I draw that 1 blank. Each blank gets 2 electrons, an up and a down arrow, so I draw those. That's only 2. I need to get to 10. So I've got to keep going on my periodic table. After I go all the way through 1s, I come to the next row. Now I'm at 2s. So I write 2s. S's get 1 blank. So I draw 1 blank. Each blank gets an up arrow and a down arrow. That's 1, 2, 3, 4 electrons. I need 10. I'm going to have to keep going. So after 2s, I'm supposed to go across. This new section is 2p. So I'm going to write 2p. How many blanks does p need? Again, if we look back in our notes, p needs 3 blanks. So I'm going to draw 1, 2, 3 blanks. Now, we have to remember the good mother rule. We put in electron number 6, or excuse me, electron number 5. When I go do number 6, remember, it can't share a room if there are empty rooms. That's not fair. If you live in a mansion, you wouldn't be sharing a room when you have all those empty rooms. So number 6 should get its own room. Number 7 should get its own room. Then only after every room has somebody living in it, then you start making them share. So that's 1, 2, 3, 4, 5, 6, 7. All the rooms have somebody. Now I start making them share by putting down arrows. 8, 9, 10. Okay, let's look at a tricky one. Iron. If you look at your periodic table, check iron's atomic number. That will be its number of protons and electrons as well. So iron, right here, has 26 electrons. That's going to take us a while. Remember, we always start with hydrogen, which is 1s. So I'm going to put 1s. Remember, s has 1 blank, so I'm going to draw 1 blank. Each blank gets 2 electrons. I put a up and a down. That's only 2. I'm trying to get to 26. So let's see, 1s moves me across, and then I come down to the next row, and that's where 2s is. Again, s gets one blank. So I draw one blank. Each blank gets 2 electrons, and up and a down. That's only 1, 2, 3, 4. I need to get to 26. So from 2s, if I look at my periodic table, I'm supposed to move across to this new section. This new section is my 2p. So I write 2p. Peanuts, there are supposed to be 3 of them. So I'm going to draw 3 blanks. 1, 2, 3. Each blank gets 2 electrons. Remember the good mother rule. Give everybody a room before you make them share. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 10. We need to get to 26. I guess we got to keep going. Looking at your periodic table, after 2p, we got all the way through the end of the row. After 2p, go to the next row. Next row is 3s. So the next thing I write is going to be 3s. S's have 1 blank, so I'm going to draw 1 blank. Each blank gets 2 arrows, 1 up and 1 down. That's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're trying to get to 26. Good news, we're almost halfway there. But we filled 3s. That was 1, 2. And there's our 1, 2 and 3s. So now I got to move across. Got to move across. And when I move across, my next thing is 3p. So I write a 3p. How many blanks do p's get? There are 3 peanuts, so I'm going to draw 3 blanks. 1, 2, 3. Each blank gets 2 arrows, but we go follow the good mother rule, give everyone a room, then make them share. Can we stop yet? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. No, we can't stop yet. We're not to 26 yet. Gotta keep going. 3p took me to the end of a row. So, again, just like if I were reading a book, when you get to the end of one row, you go down to the next row where 4s is. So I write 4s. S's get 1 blank, so I draw 1 blank. Each blank gets an up arrow and a down arrow. We're finally at 20. We still need 26, so we're not done. After 4s, if we're moving straight across, the next section we hit is 3d, which is a little weird that we went up to 4 and now we're coming back down to 3, but it's okay, just obey the periodic table. I promise it's fine. D's, there are 5 daisies. So how many blanks should I draw for D? I should draw 5. 1, 2, 3, 4, 5. Remember, at this point we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. We need 26. So at this point I only need 6 more. But I still have to keep the good mother rule in mind. Everyone gets their own room before you make anybody share. Now I'm at 25 electrons. Number 26 is going to have to share because now every room has somebody in it. Now we're going to have to share. So we go back and we put it in here. I know there's a lot going on here. I know there's a lot of parts of this page we've left blank. We left blank electron configuration and this NGC thing. We're going to come back to those. At this point, I'm going to end the video. Miss Woodlock's going to give you some time to try just electrons and orbital notation on page 34 and page 35. Okay, continue to leave electron configuration and NGC blank. These ones, leave these blank. We'll come back to those. But I'm going to stop the video here. Miss Woodlock's going to give you some time to work on it, and if she feels like you're ready to move on, then she'll start the next video after you get some practice in.